Hello, I'm very great. Just going to go through a really quick problem here for solids. I'd consider this more of a statics problem, but it's a good place to start for solid mechanics when you're dealing with, there we go, now some focus, dealing with moment. So equation and it's MC over I. Now, start out really, really simple. Let's say that you have two roller supports sitting like this, and you have, let's say, 2,000 pounds. Going down on it, and the cross section here. We will say that it is about 6 inches wide and 4 inches tall. And it's just a rectangle. And because it's just a rectangle, it means that our central axis is just going to be at 2 inches if we define this. That's our 0 at the bottom corner. Oh yeah, and then this force we'll say is acting at our length divided by 2, so right in the middle. We'll say length is equal to 48 inches. So let's try and figure out what our moment is. So drawing from here. And why don't we, before I draw this, just draw a really quick and simple free body diagram. So here's our FBD. Let's just say, looking at the y direction here, we've got 2 kips. And then we've got, we'll call this A, and this one B, FA, and FB. Pushing up. So just taking the sum, saying this is static. We can say that FA plus FB have to equal out to 2 kips. And then if we take the, why don't I just for the sake of simplicity, let's say that our supports A and B are right on the ends. This will make things a little bit easier. So next we're gonna go ahead and find the moment about A, and if A is right at 0, 0, then that means that we've got L over 2 times 2 kips. And then let's say counterclockwise is positive, so that would be negative plus arm length multiplied by the force of B. That's once again because it's static equal to 0. So nice, we can just cancel out our L's, and we'll find from the moment that FB is equal to 2 over 2 kips, which is equal to 1 kip. And FA plus FB is equal to FA plus 1 kip, and it's equal to 2 kips. So therefore, FA is also equal to 1 kip, because it's, and it makes sense intuitively because this is right in the middle, so it's evenly between those two supports. So yeah, this is our proof that FA equals FB equals 1 kip, or each of them equally distribute the load amongst themselves. So I'm just going to write this in the corner so you know. Working from here, we'll say this is our length right here. This is our length over 2. And then 1 kip, 2 kip, negative 1 kip. So what's going on here? Right at our end here, we have FA pushing up 1 kip. So we're going to go like this. And then at our length divided by 2, we have a force pushing down 2 kips. So we go down to our 1 kip, negative 1 kip. And then right at our length again, we have FB pushing up 1 kip. So always want to make sure you end at 0. Now, what's next? Well, after our force, we're going to do the equation, if I remember correctly. And for that one, we take the integral of this shape. So it'll just be the same general shape here. It'll just be linear. So we go back to that rather than just drawing a random shape here. Well, we can, if we want to just treat it this way, we can write a function of x. F is equal to one kip given that F, or not F, I suppose I should write this as equal to, let's call this lowercase l, given that L greater than or equal to 0, is equal to L2. If we take the integral of that, we will get our integral of xl with respect from 0 to L over 2. Or just from 0 to L, give us L. So we're going to be increasing in rate of L, which is how we can get shape here. And then if we do the same thing here, x L is equal to negative 1 given 0, or L over 2 is greater than or equal to L, greater than or equal to L. We can find that under that circumstance, L is equal to negative L. So we get that shape right there. Now, I'm just reusing this graph. Don't take, this is actually equal to 1 kip. This is the calc approach to it. You could also just, I remember in my solid mechanics class, something about taking the area underneath to find the size of the moment. So if you want to just take that approach, when it's nice and square like this, or triangular, as in linear with a distributed load, it's nice and easy. So that was 1 kip earlier, and L over 2. L over 2 is 48 inches divided by 2. So 24 times 1,000, or 1,000 pounds, or 1 kip. So 24 inches times that will give you, this is peaking right here, and or 24,000 kip inches. So 24,000 pound inches right at that peak. That's one way to do it. The other way you could do that with that calc approach was if we said, we ended up getting L, right, for right there. And we're saying that we're integrating from L over 2 is our boundary limit and 0. So that would give us that L, we just plug in L, so that would be what? F of L at L over 2 would be equal to that 1 KSI I previously mentioned, times L over 2, which is our 48 inches over 2, give us the same answer using the calc approach where you just say that integral of 1. It's the same approach here. So, maximum moment is 24 kip inches. If we want to put it into another, actually, you know, no, kip inches is just kind of a. Now plugging it into here, so we get our stress is equal to 24 times 10 to the third pounds inch. Multiplied by our central axis, which is 2 inches in this case, divided by 1 over 12 times the larger one of these two, so 6 inches for a rectangle, times the smallest one, 4 inches. And the smallest one gets cubed. So, why don't I move the camera down? Which gives me a stress of 1,500 pounds per square inch. Now, where could this be different? Well, some of the things that could change. What if instead of making this into a perfect rectangle like this, what if I had made it so that it was an I-beam instead? If it was symmetrical, your central axis would still lie there. But let's say that I made the bottom of this fatter. Now your central axis is not going to be in the middle, but because there's more weight towards the bottom, you're going to have your central axis be more down there. Or if I just gave you a weird asymmetrical shape, that could throw you off too. They're all things you should, like an I-beam should be relatively easy to find. If you have a book, the book will definitely go over it. Just go onto Google Images, you'll find like a million different ways showing you how to apply the parallel axis theorem to find for an I-beam where it is. Same if you have a T shape. What else can change to modify the way this problem is tackled? Well, if instead of having just singular load at a singular point, I could have a distributed load. At some place. And let's say the center of it is still at L/2. Well, what's going to change in this is this little graph right here is no longer going to be nice and pretty like this. Instead, it'll look like if we've got it somewhere away from the edge, you'll still have this support going up right here. So it'll be flat for a period. And then at some point where the distributed load starts, it will start to move down. And then at some point that distributed load ends and it goes back to being flat. And then if you've got your support at the end, it'll keep going up like this. So I don't know the slope of this. This is just an example. But let's say, well, one way you could write this is, let's say we have a function, oh, let's write it for this, a function f of L, and it's going to equal different things at different points. So I'll call this point alpha and this one omega. So before alpha, we're just going to be equal to a constant. So C1. This will be C2. So that's given that L is greater than or equal to 0 or less than alpha. Now, f of L is going to equal to negative m for our slope, because it's a linear slope. We just have that times L plus our intercept, I believe. Because we aren't just starting out at 0 here because of the support, but rather we're starting out with some intercept. Given that, finally f of L is equal to our second constant, given that L so that's how we could describe this. Let's look at this middle case right here. So let's call this cases. This could be case 1, case 2, case 3. So looking at case 1, or case 2, sorry. Looking at case 2. Integral f of L will give you negative FL squared over 2 plus BL. Evaluated, because we know our limits here, evaluated from omega to alpha. And you could use this to find your area for a distributed load like that. Now, could make it even more fun if, let's say, instead of having a rectangular distributed load, have a triangular one. And not even a nice triangular one, and that it ends off at 0. This one, you can think of as being a rectangular distributed load plus a triangular distributed load, and then work from there. That one won't be terribly fun because you're going to have a fun shape to deal with over here. But it'll be a similar principle of integrating just to find that area that the maximum is going to be your moment. Normally, you'd have one graph and then the moment graph directly beneath it, but I just didn't have space to do that over here. I hope this helped.